Let's test the world we live on, literally. No debates, no insults, no "trust me, bro." Just 10 simple experiments you can do with a phone, a stick, a few cheap tools, and a curious mind. We'll try the internet's most popular flat Earth claims and see what the measurements say. Wherever you land after this, you'll know how to test reality for yourself. Stand on a beach or big lake with a clear horizon. Zoom in on a distant boat. As it sails away, watch what disappears first. The hull fades before the mast. Bring it back with digital zoom if you like. The order of disappearance doesn't change. If the ocean were a perfectly flat plane, perspective would make the whole ship shrink uniformly. Instead, the lower parts vanish first because the surface falls away from you, curvature. A calm day with good visibility helps, and yes, refraction can bend light slightly, making the horizon appear higher or lower. But refraction can't invert the order. The bottom still goes first. Try again from a higher vantage, climb stairs or a dune. You'll see farther exactly what a curve predicts. Grab 2 sticks or meter rulers, 2 levels, and 2 friends in cities a few hundred kilometers apart. At local solar noon, when the sun is highest where you are, measure the length of each stick's shadow. Same stick length, same time, different latitudes. If the Earth were flat and the sun were distant, shadows at the same time would be parallel and equally sized. They aren't. The difference in angles equals the difference in your latitudes, which is precisely what Eratosthenes used over 2,000 years ago to estimate Earth's circumference. You can repeat his experiment with a spreadsheet, a phone's inclinometer, and free messaging. Nothing ancient about it, just geometry and sunlight. Stand outside after sunset and point your phone due north in the northern hemisphere. Time-lapse the sky for an hour. Stars trace circles around a point, Polaris. Measure the elevation of that point with your phone's inclinometer. It's nearly equal to your latitude. Travel south and repeat. The angle to Polaris drops. Cross the equator and Polaris is gone. New circumpolar stars appear around the southern celestial pole. On a small flat disk with a tiny local sun, fixed Polaris visible everywhere doesn't make sense. The changing star maps with latitude are exactly what a globe predicts. Pick 2 places separated east-west. Watch the sunrise live on a webcam in one city while it's still dark in the other. Or coordinate with a friend 1 time zone over. Text when your sun touches the horizon. They won't see it for another hour. Time zones aren't arbitrary lines. They're reality's sync signal, Earth rotating, sunlight sweeping over a sphere. If you fly long haul in the southern hemisphere, check the Great Circle map versus the straight lines on a flat map. Flight skews shortest spherical paths, not flat straight lines that would be wildly longer. Hold a small ball and a lamp in a dark room. Put a sticker continent on the ball. Walk the ball around the light. Notice how day and night sweep in a great circle. Tilt the ball and watch seasons emerge. Longer days in one hemisphere, shorter in the other, with equinoxes when both halves share day evenly. Now try to make a lunar eclipse. Put a second smaller ball behind Earth and line up Sun, Earth, Moon. The shadow you cast is a clean curve no matter the angle. That curved shadow on the Moon during eclipses is a nightly receipt for a round Earth. It's been observed by every civilization that watched the sky. Stand under satellite dishes on rooftops. Notice how they point, not randomly, not straight up, but at a specific belt in the sky. Move across a country, they all point toward roughly the same region near the equator. Geostationary satellites hover over the equator relative to the ground, and dishes lock onto that arc. On a small flat plane with a tiny nearby dome, Universal pointing toward a distant equatorial ring doesn't fit. If you have a compass app and a clinometer, you can record azimuth and elevation of several dishes and triangulate the belt yourself. Set up a tripod on a balcony with a clear skyline and film the sun setting. Watch how the sun disappears. The bottom edge kisses the horizon first. The disk flattens slightly near the horizon because of atmospheric refraction, and then the top rim slips away last. If the sun were a small lamp moving in circles above a flat plane, the disk should grow smaller with distance and move toward the horizon without actually setting behind it. But it doesn't shrink to a point. It stays the same angular size all day and sets behind the horizon with clear occlusion. Try a sunrise as well. The behavior mirrors. Make a Foucault pendulum visit part of your next city trip. Museums and universities often have one, a long pendulum that swings in a fixed plane while the floor beneath rotates with the earth, causing the swing direction to slowly precess over hours. Near the poles, it completes a precession in about 24 hours. At the equator, it doesn't precess. You can also test rotation at home indirectly. Record star trails over several hours. The entire sky appears to rotate around a point. A rotating sky dome could mimic that locally, but then wind patterns, Coriolis effects, and flight paths would disagree. They don't. Meteorology, ballistics, and navigation all use Earth's rotation because it works. Print 2 photos of a city skyline from across a wide river or lake, one from near the water, one from a high overlook. On the low shot, draw a line along the visible base of the far buildings. Some lower floors are hidden. On the high shot, more of the lower floors appear. There are entire communities who repeat this with lasers and targets, arguing over refraction and level. Here's the crisp version. Water finds an equipotential surface under gravity, and on a globe that surface is curved. Over long distances, the geometric drop is predictable, about 8 inches per mile squared, approximately 7.8 centimeters per km squared, with corrections for refraction. Your 2-height test dodges the laser refraction fight and shows the same principle. Higher vantage, farther horizon, more of the hidden base revealed. Open a flight tracker and compare distances and durations for routes like Santiago-Sydney, Johannesburg-Perth, and Buenos Aires-Auckland. On common flat Earth maps, these routes would be enormous, sometimes longer than their northern hemisphere equivalents. In reality, they're flown daily within times and fuel loads consistent with great circle distances on a sphere. Also, note non-stop polar or near-polar flights like Auckland-Doha, which take the arc you'd predict on a globe, not the zigzags you'd need on a disk. Airlines don't gamble their margins on bad geometry. Pull up long exposure photos of the southern sky from Australia, Chile, or South Africa. Stars rotate around a point in the south as cleanly as they do around Polaris in the north. On a single-pole flat model, it's hard to explain 2 opposite centers of rotation that stay put relative to local observers and star patterns that are consistent across continents. If you're in the south, time-lapse it yourself. The center of rotation sits near the Southern Cross region. Northern and southern star maps aren't opinions, they're reproducible. Let's talk gravity without jargon. Drop a phone and a ball at the same time. They accelerate together. Density and buoyancy explain why things float or sink in a fluid, but they don't supply the downward acceleration that gives up and down meaning everywhere. Gravity does. You can watch tidal forces in real time. Tides rise and fall predictably under the pull of the moon and sun, with timing and amplitude matching models of a massive Earth-Moon-Sun system. If you live near an amphidromic system or a strong bay, the lag between moonrise and high tide is a neat local demonstration. Gravity on a sphere also explains why the sea surface bulges under the moon and why that bulge follows a path across the globe that mariners have charted for centuries. Common objections deserve straight answers. If Earth is round, why can't I see the curve? Because you're small compared to the planet. Over 10 kilometers, Earth drops about 8 meters relative to a tangent line, visible with careful instruments, not with naked eye intuition. From an airplane, the curve is subtle because your field of view is small. Wide-angle lenses make it look extreme. Telephotos flatten it. That's why we do measurements rather than rely on vibe. But the horizon looks flat. On a sphere, the horizon is locally flat, the same way a huge ball looks flat to an ant. Water finds its level. Level means perpendicular to gravity, an equipotential surface which is spherical around a mass, not a flat plane stretching to infinity. What about NASA faking photos? Space agencies aren't the only cameras pointed outward. Weather satellites from multiple countries deliver imagery used daily by pilots, meteorologists, and TV weather forecasters. Private companies run satellites. Amateur radio operators bounce signals off the moon. Backyard astronomers photograph the International Space Station transiting the sun. The system is too large and too international to reduce to a single source. But even if you distrust every space image, none of the 10 tests above rely on orbiting cameras. They're local, cheap, and yours to repeat. Perspective is real and powerful, but it's not magic. Train tracks meet at a vanishing point because lines in 3D project onto your eye's 2D plane. They don't actually meet. On a flat plane, perspective makes objects shrink uniformly with distance. It doesn't make lower parts disappear sooner. Nor does it create time zones, 2 celestial poles or different star catalogues by latitude. Perspective explains why ships appear smaller with distance. Curvature explains why their bottoms go first. Atmospheric refraction matters. On rare days, cold layers of air over water can bend light dramatically, creating mirages that float ships above the horizon or lift hidden features. Those are fascinating edge cases and documented as such by mariners for centuries. Refraction is not a blanket excuse. It's a measurable effect that can slightly shift where the horizon appears. That's why repeatable experiments use multiple days, multiple heights, and, when possible, infrared or narrowband filters to reduce haze. The pattern stays. Curvature signatures persist across conditions. If you want the cleanest, home-friendly demo of Earth size, coordinate an Eratosthenes day. Recruit viewers from different latitudes. On a chosen date, measure the sun's elevation at local solar noon with a stick and tape measure or a smartphone inclinometer. Share your latitude, longitude, and shadow angle. Plot the data and fit a circle. You will recover a circumference within a few percent, limited mostly by your equipment and alignment. It's one of the most beautiful citizen science projects you can do. No permission, no big budget, just sunlight and geometry connecting strangers across a planet. For rotation, try star trail photography anywhere with dark skies. Fix your phone on a tripod, use a long exposure app, and stack frames. In the north, the trails form concentric circles around Polaris. In the south, around the southern celestial pole. At the equator, stars rise and set in straight lines perpendicular to the horizon. Move latitude, and the picture morphs exactly as spherical geometry predicts. It's addictive once you see it. Curiosity beats teams. People adopt flat Earth ideas for many reasons. Distrust, a desire to question authority, the thrill of seeing through the mainstream. Questioning is healthy. The cure for bad answers isn't shame, it's better questions and clearer measurements. Try the tests, Post your results and be specific. From 2 meters above sea level, I could see X at eye distance, or at 40 degrees N, Polaris sat 40 degrees above the horizon. The more local, the more boringly precise, the better. If you want more wow, look at eclipses and long-haul flights. A solar eclipse's path across Earth matches the geometry of a moon casting a moving shadow on a rotating sphere. Predictive websites tell you down to seconds when and where to stand. Stand there and watch the moon's shadow race over you at thousands of kilometers per hour. Meanwhile, flights planned using spherical trigonometry arrive on time. If Earth were shaped differently, global logistics would fail spectacularly. They don't. Shipping lanes, satellite links, fiber optic cables, undersea charts. These complex systems agree on the same geometry because it's the geometry we live in. You don't have to become a geodesist to see it. Measure shadow angles in 2 cities. Film a ship from 2 heights. Time-lapse the northern or southern sky. Note dish directions. Watch a sunrise across time zones. You'll end up with a scrapbook of small, concrete facts. Together, they point to one shape. Not because some authority said so, but because the measurements you made, in the places you live, with the tools you own, converge. That's what science is, not a pile of quotes, but a network of observations that fit together. The Earth can feel flat beneath your feet and still be round. Human senses evolved for hills, not horizons. That's why experiments, humble, repeatable, slightly nerdy, are the antidote to grand illusions. Try 2 of these this week. Post your numbers. If you've never done a citizen Eratosthenes, organize one in the comments. The planet won't be offended if you measure it. It's been round the whole time. Now you can see why.